In this application of the definite integral, we're going to look at the concept of net change and how net change can be related to a definite integral. So what do we mean by net change? So for instance, graphically, if you have a function that does something like this, and let's say the interval there is from a to b, right? So we can say as x changes from a to b, so as our independent variable x changes from a to b, this is how the y value changes, right? It changes continuously. Sometimes it goes up, sometimes it goes down. But we can say that, again, over that interval, the net change in the function value is simply that difference, right? So again, over some parts of the interval, the function value is increasing, and some parts it's decreasing, like right here, decreasing again right here, increases kind of sharply there, and decreases sharply there, and eventually, so even though the y value is changing continuously, we could say over that fixed interval, right? We could say that so as x changes from x equals a to x equals b, the net change in the function, right, is simply a difference. It's f of b minus f of a, right? So for instance, just as a brief example, if our function is y equals x cubed minus 3x squared plus 1, and let's say the interval is from -1 to 2, then I can compute the net change. Now, there is a symbol that we use for net change, and in math, science, technology, we typically use the letter delta to represent the change, and we've seen that before, like in our delta x for a Riemann sum. But here now it would be delta y, and then to indicate the interval, you can put it using the interval notation right below it, right? So all the symbol means is the change in y over the interval from x equals -1 to x equals 2 is, and it's just algebra. You would take y of 2 minus y of -1. So y of 2, that will be 8 minus 12 plus 1, and then minus y of -1 would be -1 minus 3 plus 1. So what do we end up with? So this is 9 minus 12, so that's -3 minus, and look, we have another -3 there. So the net change of this function over this interval is 0, right? It's certainly not a constant function. It's a cubic polynomial, but over this particular interval, the net change is 0. So graphically, what that means is the function might do something like this, like start at a point here, and then it changes, and then ends up at the exact point there, right? Or similarly, it could start here, go up, down, maybe fluctuate, and then come back down here, right? So our net change is 0. And I just want to point out, do you notice this difference? This idea of taking one function value and minus another function value, that should ring a bell. We've done that recently with the fundamental theorem, right? So the question is, why are we doing something like this in a calculus? class, right? There's no calculus here. You have a function, you evaluate the function twice, and you take a difference. So obviously we need more to this application before we can call it an application of the definite integral. Well, this is the thing. Suppose you are not given y equals f of x, right? So suppose you're not given the original function, but you're given the rate at which the function changes, right? So if y of x is not given, but instead the rate of change of y, so the rate of change of y of x is, right? How do we find the same delta y, this change, net change in y, right? So how is delta y computed, right? So in other words, if we're given the rate of change, well, what is the rate of change of a function? That instantaneous rate of change is the derivative, right? So the rate of change of y, right, is y prime of x. So in other words, if you're given the derivative, how could we find this net change? Well, let's see if we can work backwards. So we know that the net change of the function, so now we're going to write it a little bit more generally. So over this interval, let's say x0 to x1, we know that the change in the original function, like that, is simply like, if we knew y, right, then it would be y of x1 minus y of x0. But we don't know y, we know its derivative. So the question is, could we set this difference up as like a definite integral maybe? So like working backwards, pretend that this is like after you've computed the definite integral and you've used the fundamental theorem and you've taken the difference. So we know that this function y would be the antiderivative of the function we would have started with, right? So then what would that function be? So what would the function have to be so that when I integrate it, I get y? Well, that would have to be the derivative. So this difference, this net change, can be written, this is the calculus version, the calculus formula of this quantity. It's the integral from x0 to x1 of y prime of x dx, right? So these are saying the same thing, right? And they're equal due to the fundamental theorem of calculus, that part 2, right? So these two are the same because of our FTC part 2. And all you have to do is look closely at this definite integral and see that it works. Because in order to compute this, we would have to integrate the function here. Well, when I integrate the derivative, I am going to get the original function. And then the FTC part 2 says plug in your upper limit into that original function, which is this. Plug in the lower limit into that original function, which is this, and then take a difference. So in words, what this is saying down here is if you integrate, so if you integrate the rate of change of some function, so the rate of change of a function over an interval, so if you integrate the rate of change of some, let's say, quantity over an interval, you're going to get the net change of that quantity over the interval, right? So you get the net change of the quantity over that same interval, right? So again, it's not a difficult formula. Again, let me write it on this side a little bit more clearly. So now if I want to get the change, net change in a function, and I happen to have its derivative, all I have to do is integrate the derivative from x0 to x1, and that will give me what I'm looking for, right? So that's one thing. So this is the, again, net change. Well, there are some other problems where you're not just looking for the net change, but you're looking for like a final value, right? So what I'm going to do is take a look at this equation right here. So I'm going to write these two, and these are equal, right? So since y of x1 minus y of x0 is equal to this integral, so y prime of x dx, let's say, for instance, that this is, yeah, so this is the net change, which is also like this. So if I wanted to solve this equation for y of x1, so add y of x0 to both sides. So y of x1 is equal to y of x0 plus our definite integral, right? So this is just another way of writing the same equation. But when I look at this, this is almost like saying, here is some initial amount. Remember, it's like, you know, something that's changing over time. So here is the initial amount. This is the net change, right? So all of this is the net change. So how much does the function, the quantity changes? By what amount does it change over this interval? If I add these two together, then this will tell me the final amount that's present at the end of that interval. So this will be the final amount, right? Yeah, so if you know your starting value, how much is there at a certain time, and then by how much does the quantity change over some interval, and you add those two together, you're going to get the final amount that's there at the end of that interval. And there's a shorthand notation that's sometimes used for something like this, and the shorthand is just abbreviate this as y sub 1, that's your final amount, and then abbreviate this as y sub 0, that's your initial amount, and then your change is, so the integral from your final x to your initial x, and you integrate your derivative, right? So there are lots of ways this equation can be used. Believe it or not, this equation can even help you solve certain initial value problems, right? Which we won't get into in this particular video, right? But let's see how this concept can be implemented by looking at a few examples. So, all right. So the first one is just, the first example is going to ask you about the net change. So let's say we have something like this. So water flows into a barrel, right, at a rate of, so let's say this is W for water, and the rate is given, that's the key. So the derivative is given, and let's say it flows, and this is the, so like the square root of t plus 1, and let's say this is at a rate of gallons per minute. So gallons per minute, right? How much water, so here's our question now, how much, so that's the quantity, how much water flows into the barrel, right, in the first, let's say, 4 minutes, right? So that's a typical sort of question. You have water or some quantity that's changing over time, but what you're given is the rate of change of that quantity. In other words, you're given the derivative, and then you're asked how much of that quantity, or by how much does that quantity change over a certain interval. All right, so let's see the solution for this. So first let's write down our derivative. It's the square root of t plus 1. And then let's see what the interval is. Now the first 4 minutes, and our rate is per minute, so all our units are consistent. We don't have to worry about changing the units. Well, the first 4 minutes, that's from 0 to 4. Not 1 to 4, but 0 to 4. The first minute is from t equals 0 to t equals 1. So the first 4 minutes will be from t equals 0 to t equals 4, right? And what the question is asking symbolically is this, right? What's the change in the water flowing into the tank, so over this interval 0 to 4, right? And the key is that we now need a definite integral to compute this. So this is the definite integral from 0 to 4. I'm going to integrate this function, so I'm going to write it as t to the 1/2 plus 1 dt, and then again use our fundamental theorem. So let's see what we have. So this is 2/3 t to the 3/2 plus t, and this is evaluated from 0 to 4. Right? So now we're going to do our fundamental theorem. So we have 2/3. When we plug 4 in, that will give us 8. And then plug 4 in there, that's another 4. And then at the lower limit, both terms evaluate to 0. Right? So this is 16/3 plus 4. Well, and 4, so that's 12/3. So this is 28/3. And then the units would be just gallons, right? It's not a rate anymore because we've integrated that rate and we've just gone back to the quantity, right? So in the first 4 minutes, 28/3 gallons of water flowed into this tank, right? So pretty straightforward, but the key is recognizing when you're given the rate of change and then you're asked to find the net change, right? Other example, and this one's not, there's no little story beside it, but let's say we're given like 0, 1, and we're given dy dx is equal to, let's say, e to the 2x, and the question is, what is y of 2? right? Now, like I said, you could approach this from an initial value standpoint, but I'm just going to show you how we can express our entire answer using this idea of initial and final and net change, right? So this is the rate of change. This is telling me that y of 0 is equal to 1. So this would be the initial amount. This is the rate, that's the derivative, so this is the rate of change. And what we are asked to find is what is the final amount when x is equal to 2, right? So what is the final amount when x is equal to 2, right? So in terms of the last formula that I wrote down, let's see if we could do it. So we want to find y sub 2. So that will be y sub 0, the initial amount, plus the change over the interval from 0 to 2. But that change can be written as a definite integral. And what do we integrate? We integrate the rate of change. So this is e to the 2x dx, right? So again, the final amount, right, is equal to the initial amount plus the net change. And this is where we use our calculus, right? So this is what we want to find out. We know that y sub 0, or y of 0, again, this is just a shorthand for this. We're given that that's equal to 1, right? So here's how we can set up our final amount as a single expression, where you add the initial amount to the net change. So let's evaluate this definite integral, again using our FTC, and see what we come up with. So it's 1 plus integrating e to the 2x gives us 1/2 e to the 2x, and then we evaluate from 0 to 2. And then this would be 1 plus, and then we have 1/2. Plugging in our upper limit gives us e to the 4th. Plug in our lower limit gives us e to the 0, which is 1, and we take the difference. So we have 1 plus 1/2 e to the 4th minus 1/2. So this simplifies as, so we have 1/2 plus 1/2 e to the 4th. So this is the final amount at the end of this interval from 0 to 2, right? If this were like y of 3, in fact, let's set that one up. So what if we wanted to find y of 3 instead of y of 2? Well, it's just a matter of now, so this would be y sub 3. We would still have the same initial amount, and then what I would now, my limits of integration would go from 0 to 3. And it would still be the same rate e to the 2x, because that's the derivative, right? And then we go through this process again. So let's plug in the numbers. Our initial amount is still 1. The antiderivative is still 1/2 e to the 2x. So all that changes is that upper limit, right? And then let's simplify. So we have 1 plus 1/2. At the upper limit, we'll have e to the 6th power. At the lower limit, we have e to the 0 again, which is 1. So now we end up with this as our final amount. So it's now 1/2 plus 1/2 e to the 6th, right? So again, when you look at the computation that's involved, there's nothing really new. New in the sense that, okay, it's a completely different There's not a new process. It's just a different way at looking at the concept of net change. And since the fundamental theorem already gives us a difference, what we had to modify was, okay, what do we have to integrate to get that net change? And the answer is the rate of change, which is your derivative. All right. So think on these things, and I know with some practice you'll master them. Right. And I'll see you in the next video.